key error change with cited that we spent last time on has been merged, closed, and it's already tested that it actually helps us with our problem a lot.
Great.
So thank you for that.
So if that was the biggest speed bump to upgrading to Python 3.16, we're in a pretty good place. Okay, so this one's done. Remove it from my notes then. And now this one. Okay, so we want to explain how the fix works here, right?
Yes.
Okay. How do we do that? So can I still draw on my screen? Not like that. Yeah, good. Okay, and let's try this then. Okay, so test thread state ensure is flaky on Fedora Linux S390X. And what does test thread state ensure do? Well, the fix is in testembed.c. Let's look there. And that was do tstate ensure. And of course, it's better to be on the main branch. Okay, do tstate ensure. This is used in test thread state ensure. And test thread ensure tests API like PyInterpreter guard from current, which was added recently.
Yes, 788.
PEP 788. I don't know how much you know about this PEP.
Not much, just that it exists.
Okay, so what does this do? So let's try to read the motivation and see if there's anything to explain. Hopefully there is. So many large libraries might need to call Python code in highly asynchronous situations where the desired interpreter may be finalizing or has already been finalized, but want to continue running code after invoking the interpreter. Does that make any sense at all?
Highly asynchronous situations make sense. Does that inherently mean that you have more interpreters? So you say the desired interpreter?
You don't need to have more interpreters, but you probably want an application with more than just the Python interpreter.
Mm-hmm.
So let's do an example here. So you have a graphical application with like a window, and this window manages some kind of list of items, right? Whenever you click this little plus button, it adds a new item. Whenever you edit it, it edits that item, and so on. And this thing has nothing to do with Python, but it has a little Python plugin which keeps a list of these items as, I'll say a list of strings, right? So whenever you press this little plus button, a new string appears in the list, right? And this is a plugin that you can load and unload at any time, right? So there's some kind of event handler on this button that will see if this plugin is enabled, and if it is, it'll activate Python, find this list, add a string to it, and be done. Right? Now, when you unload this plugin, Python will deinitialize. So there's no more Python here. But if this event handler on the plus button was running at the exact same time, it would try to manipulate the list while Python was being destroyed, which is bad. So this is one example of what this pip does, right? So with this pip, what the event handler now can do is take a guard on the interpreter, saying that while this thing is active, I don't want anything to happen to my interpreter. Then do its thing, find its list, manipulate it, and then release the guard. Right?
Regarding the naming, is guard and lock semantically different, or is it just two words to describe this same kind of situation?
So basically, what those do depends on the particular thing you're talking about, like their generic terms. In this case, it's probably better to call it a guard. I would have liked if it was called a reference, but that didn't go through. So lock kind of implies that you have exclusive access to something. While a reference, at least in Python, is used for you not having exclusive access to something, but you want that thing to stay alive. And that's what these guards are.
Okay, I understand.
Right? Okay, so that was an example. This is what has been brought up by users. For example, a callback that wants to call Python code might be invoked when some GPU computation finished running, network packet was received, a thread has quit and wants to finalize something, or you click that button. Right? So generally the pattern would look like this. There's some callback. You do pyguild state ensure, invoke the CPython, because pyguild state ensure basically logs the GIL in traditional Python. Right, so you call this, you now have access to Python CPython, then you release and you're done. This is a problem because if the target interpreter is finalizing, and that might be the main interpreter, aka Python itself if you just have one, that can also be finalizing. And the behavior of this function is such that if this happens, the current thread will hang. Before it just crashed, now it just hangs because that's better than crashing. Or if the interpreter has been completely deleted, so no more data is there, everything has been deallocated and freed, then a dashing will probably crash anyway. Right? So if you're just targeting a sub interpreter, then data about that is still around, so we can hang, otherwise this will probably crash. And there are currently a few workarounds, but they're not that great. And when we try to explain these workarounds to people, they always find some holes in them. So yeah, this is each option generally work, but can be verbose, complex, or results in other issues. That's very charitable phrasing. I would say these options can theoretically work, but I haven't seen a working implementation that's like safe from all the edge cases. Basically this is a good pet. And what it does, it adds APIs. There's a PyInterpreter card, which is like a token that if you hold it, an interpreter will not finalize. So whenever you call PyInterpreter finalizer, whatever the API is finalizing, that will hang the thread that wants to finalize that interpreter until all the guards are released. Or close, that's the terminology here. So you can get a guard from the current interpreter, you can get it from an interpreter view, which is coming up later, and you can close it. Right, so very simple API. Then there are interpreter views. So in our situations, our example here, the callback or the code around the callback cannot have an interpreter guard, because you do want to be able to remove that Python plugin, deinitialize Python. Holding a guard would prevent that, right? So instead of having a reference, so I would like to call it reference. So instead of you have a view, which is like a weak reference. I don't know if you know about the weakref module in Python.
I know it exists.
Okay, so weak references are objects that have one operation, and that operation gives you a strong reference to some object. Or it gives you none if that object no longer exists. Right? So a weak reference is something you can ask for a strong reference. Once you do, you now safely have a strong reference that's preventing that object from going away. Or you get nothing, and the object is no longer reachable. Right? So what this callback will have is the view, and whenever the callback is invoked, it'll get a strong reference to this Python thing, and if it can't do that, it'll do nothing. Right? So that's interpreter views here. Again, we have a type. We can get it from the current interpreter. We can close it, and there's this legacy function to get a view for the main interpreter in case that's a special case. So does this sound reasonable?
Yeah.
Alright, so once you have a view, you can use this PyInterpreter guard from view. You have a strong reference. So this PyInterpreter view from main is there because not all callbacks have like state that they can use. Right, so if this callback is just a C function, it doesn't have any idea of the specific interpreter it wants to work with.
Mm-hmm.
Usually nowadays when you have a callback API, it'll have like a opaque argument where you said, whenever you call this callback, I want this piece of data to go with it. So let's see, SQLite CAPI. Does this have callback? There is a callback function called to SQLite 3 exec. So there's some SQLite function that allows you to specify a function that it'll call whenever something happens, and that function will get as its first argument some piece of data.
Mm-hmm.
Right? I don't know what this callback is for. It's probably when the data is ready, this function will be called, and you pass in a piece of data that the function then gets, right?
Mm-hmm.
Because it's just a pointer to anything, you can put any kind of data in there, and in our case you would put in the interpreter view and any other data you want, right? So modern callbacks in C work like this. If you have some older library that doesn't do this, then that's what this function is there for. You're limited to the main interpreter, but you can still get a view from nothing.
Mm-hmm.
Right? And then we have more API. We have pythreadstate ensure, which basically logs the GIL and ensures you can now call Python APIs. Ensure from view does the same thing, but it creates a temporary guard while that thread state is active, and you can release that, right? Mm-hmm. So attaching a thread state is equivalent to getting the GIL,
mm-hmm.
except you can have more of them at the same time attached. Right, old API is deprecated, and that's it. It's really a very simple but explaining it to people who don't know this is was very hard. And also coming up with the naming, which I still don't agree with, but right, so anyway, that's what was added, and that's what this tests. So what do we have here? Some kind of initialization, kind of internal assertion for internal state. We get a guard from the current interpreter. Right, so initialization here will spin up Python basically and give you a current interpreter and attach thread safe states and so on. So all the tests basically have normal Python to work with. So we get an interpreter guard from the current interpreter. We assert. So normally you'd have error handling here. This is a test, so if this doesn't work, the test fails. There's some data for the callback.
Mm-hmm.
Then we, not for the callback, for the thread. So then we start a thread. So this, I assume from the name, starts a new thread and calls this function init.
Mm-hmm.
And passes data as an argument. So this is a pointer to whatever, and the function will then take it and cast it to do the same type. And this function will fill in the thread ID and a handle. Knows what that is for, but it's needed. So if that doesn't work, then the fit test fails. Now we hold an interpreter guard, which means this PyFinalize will block the main thread until that guard is released. Right? After that, we assert that this data.done was set to 1. So what is this thread data? That's this little struct there. There's an argument, there's an int done, and there's an event. Right, so this is just the data that the two threads use to communicate. So it's initialized, so just the argument is initialized here, this guard. The other ones are left at 0. Right. So this is a bit tricky in C. If you just do this, then the variable will not be initialized. But if you initialize it, then all the elements you leave out will be set to 0. When things will be set to 0 and when not, it's probably better to check each time you do this. But in this case, they are set to 0. Right, so we finalize, we assert that the thread actually was done, and then we join it. So this waits until the thread is done, basically. Right? And what does the thread do? It will take an argument, do pythread state ensure like 4 times, do pygil state ensure, then it will run some thread code which computes Fibonacci for a bit, then it will release all the guards and then the guild state, and it will mark things as done, and then it will close the guard. Right? So all of this pythread ensure is redundant. This pygil state ensure is necessary for pyrun simple string to be valid. And we basically test that you can do this multiple times as long as you then release everything properly. Right. With the current implementation, you could even release it in the wrong order, nothing would happen, but don't want to test for that. And so these are basically like contexts, right? You have to pair each creation with the corresponding release. Something like this. Right. Okay. So the problem here was that these two lines were switched. So PyInterpreter guard close happened here, but on the mainframe architecture, apparently this made PyFinalize go ahead. So the Python was finalized, and then this assert happened. So we asserted that the data is done, which failed.
It wasn't.
Because we didn't get to this line yet. And the other third. So hopefully that makes sense now.
So just to reword it, PyFinalize is basically a signal for the interpreter to shut down. But
That's the function that shuts it down.
But it doesn't shut down because we have the guard, which is this improvement, and this is what we test. So that it holds until the things inside are not done.
Yes. So the first thing PyFinalize does is wait until all the guards are gone.
And the guard was
here.
going in the second to last line, basically, somewhere there. I'm surprised that worked on the other architectures?
Yes. I'm actually surprised that it failed on one architecture, because usually thread switching doesn't really happen that often,
Mm-hmm.
right? It's so all these race conditions you keep hearing about, where the thread switches at exactly the right time. Those are very hard to get in practice unless you have a giant fleet of servers and things run them there all the time, right? So usually on a normal architecture, uh, or well, not the Fibonacci, but all of this would just run in one go.
Mm-hmm.
But apparently on the mainframe, something about this PyInterpreter guard close, well, because what the PyInterpreter guard close needs to do is set a signal. Because if the finalizer was waiting, it needs to be woken up,
Mm-hmm.
right? So apparently on the normal architectures, waking up another thread just tells the kernel that it's okay to wake this thread up now. But on the mainframe, there was apparently a higher chance of the kernel switching to that thread immediately after that thread became runnable.
Mm-hmm.
Which I guess makes sense if you think about it. Somehow.
It kind of leads me to another curious question, which is not that much related to Python, but more to the architectures themselves. Uh, is it possible um, to somehow list like very typical differences, practical differences that happen between the most popular architectures, some gotchas that always happen? You always know that this kind of architecture does this thing differently. I know about endianness as a concept, but I am not familiar with the rest. Maybe that's not a question for here and now, but I got very
Uh,
curious.
yeah, I don't think I can make a list. But whenever you hear something like, this could happen maybe, and you don't see it happening on your machine, then it's probably happening on some other architecture.
Mm-hmm.
And if not, then we probably assume that it will never happen. Like there are several places in the CPython source code where we assume that a pointer has either 32 or 64 bits, just because we cannot test on any other architecture.
Mm-hmm.
There's a few things like that where once we can test it on some other architecture, it will be relatively easy to port there, but the hardware doesn't exist.
Mm-hmm. Um, don't bots cover a wide range?
Yes, they do. They do, and like external projects cover, like run their test suite on even more architectures. So whenever we break something, we usually hear back. For example, there is one architecture where the stack grows the opposite way. Like
Mm-hmm.
the function call stack, like the piece of memory where arguments and local variables are put. So usually it goes from bottom up, so from high addresses to low ones,
Mm-hmm.
which sounds counterintuitive, but you have to have the stack and the heap at basically the opposite ends of the memory, so they can meet in the middle. So one of them grows one way, the other one grows the other way. And on some architectures, it grows up, and that failed, and somebody complained, and some weird deep internals had to be fixed.
Mm-hmm.
And the fix was relatively easy, or at least it looks straightforward when somebody figured it out. The hard part is testing it, getting at least an emulator.
Mm-hmm. So.
Right, so anyway, all of this Pythread and stir was a detour basically. Could get the same thread condition even with just deleting it, but it was a nice detour.
Yeah. Thank you for the explanation. Now I understand what's happened. And it wasn't always happening. Even on that's single architecture, it was
Interesting.
once in a few rounds.
Well, I guess it depends on this interval guard close waking up the other thread immediately. So probably you need to have an idle CPU or so where the kernel would basically schedule the other thread on that CPU and go through all of PyFinalize and then get to the assert before it was done doing this. Before it returned from the PyInterpreter close and got back to the store.
Mm-hmm.
Which, I'm really surprised that happened. But right, so what else should we look at?
Do you have anything, maybe? I don't. I know that there is beta 3 released, but I haven't had a look at it yet. Oh,
yeah, that was just released. So do we want to take a look at this one?
Let's look at this one.
Lazy imports. So Fedora has this check import, right?
Yes, we do.
Where is that again?
It's in Python RPM macros, and it's unfortunately only on source Biscuit.
Python
RPM
macros.
Yes. I still haven't upstreamed it, but it's import all modules Py, basically. So this is the script that figures out what it needs. And
right, so should we work on this for 20 minutes? Does this have a test? Oh,
it
yes, it does.
It does. And now we have even Fedora with Python 3.15 as the main one, so it's testable.
Okay. So macros.
Yes, there's import all modules and test that.
Yeah, I like to open a file from the root of the repository so my file list works well. And then, okay, just import all modules. Let's see.
Yes, there's a few test cases with mocked a bit mocked environment. We want to create some files on the temporary paths and write something in them. And I think the test for that would also have to create a file on a temporary path and write some text in it, like something. Oh, that's okay. It's even because we need first a Python file and
what am I looking at? Import all modules.py.
so that's probably too late.
Test import all modules.
So we tried to. Where did we assemble all modules? No, we did it while saving files. This PyProject save files macro, and that one determines what files are in the package and what modules are in the package, the Python files. And it collects the list of names, and the list of names of those importable modules of the package is then given to import all modules. This tries to execute them, and everything what is in the
right. Yeah, that makes sense.
So we would have to mock a Python module containing maybe a lazy import or some combination of lazy and non-lazy imports, and then put the name of that file to or maybe we don't. Maybe it's okay if we just keep them. I don't know. I wrote it like 3 years ago.
Let's see. Test only top level included modules found. Oh, so it. Oh, that's how this looks like a good test to copy. Test. Right, so we want lazy imports to be imported.
Yes.
So how do we do that? So since only top level modules are imported here, we can make a nested module so this would have init.py the text I don't know if you do this or something else to get the indentation right. So this would, oh no, we can do this. Lazy import nested dot test, what's it called? Test module lazy import test module dot submodule. Right.
Mm-hmm.
And then we would have submodule.py with nothing in it. And we do this modules main. We don't need the rest. Append to path, we do modules main, test module.
Mm-hmm.
Like that. And we assert that test module is in sys.modules and that test module.submodule also is there. Right?
Mm-hmm.
Okay, now how do I run these tests?
That should be possible with just PyTest invocation, but Python-m PyTest.
Ah, nice.
Yeah, and this is not good.
Okay, I want just the lazy, right? Okay, what if one failed? So this is the one. I probably messed up the modules main thingy.
Modules main, and this takes a well,
I want temporary path, put it in syspath, modules main with the submodule, which has init.py in it. Okay. Failed module. Oh, something failed. Nice.
yeah, and we are not in Python 3.15, so the syntax is unknown and it does weird thing.
So I need Python 3.15 and I need PyTest for Python 3.15, so I need
yes, and that's
virtual fair. And I need virtual for Python 3.15. Okay, nice. We get an assertion error.
yes, that's
perfect. We probably want this to work on all Pythons, so we'll use the alternate syntax or alternate way to do lazy import, which was pip810, and there was some dunder lazy modules. So if we do lazy modules as test module.submodule, we should get the same effect. No, needs to be set before the import. Yes, right. Right, so we get an error, and on an old Python, everything works, right?
Alright, how does it work with old Python? It's just...
So, the pip that added explicit lazy imports adds a special magic global variable called lazy modules, which is compatible with the older syntax. Right, so if you have an old Python, this does nothing. If you have a new Python, the normal import statement will look at the lazy modules variable from the module where it's importing from, and whatever's in here, it'll import lazily.
Ah, great. So
this will work as is on an older Python. We don't need to skip it. But on a new Python, it'll currently fail.
Yes.
Which we want to fix. And how do you fix this? Import modules.
So we import modules, and we call the import module for each detect module. But I guess the issue is with the detection, because we already give it the list.
Yes.
And we have to...
Well, so this imports the modules, and it also imports anything that these modules import directly, which is what we want to test. So if they do a lazy import, that'll create an entry in a list somewhere, and we need to go through that list and import all those modules for real. And that list is named sys dot
lazy modules.
Lazy modules. All right. Okay. So I don't know if sys.lazymodules includes modules that were already imported.
There is a gotcha there. I was looking at it. Lazy modules is a set of fully qualified module name strings that have been lazily imported in the current interpreter, but not yet loaded. When a lazily imported module is accessed for the first time, its name is removed from this set.
Okay, so when it's accessed for the first time, I don't think just an import will do the accessing. So let's do this. Do this try. Probably want to go before the import. So this, yeah, this while is a bit scary. Because if there's any error in this code, it'll just loop forever. So what I like to do in tests like this is give it a bounded number of iterations.
Mm-hmm.
Now it'll fail. So what's the problem here? Lazy modules. Oh, I'm importing module, not lazy module. No, let's make the loop exactly the same. Okay, that's too much maybe.
Glob is not a package.
Oh.
It's not a package.
Oh. So apparently sys.lazymodules has more than just modules in it. Well, that sucks. We failed to import inspect.isGenerator function. Colorize can colorize get theme, glob.string globber. Ah, well that sucks. Okay, so this won't be as easy as as I thought. So the module name is added to sys.lazyModule as a set of fully qualified module names which have been lazily imported at some point. And that's just a set of names. Let's look at the actual documentation. And 315.
Yeah, that's where I...
So it should be a set of fully qualified module name strings, and inspect.isGenerator function is most definitely not a fully qualified module name. Neither is global, no recurse symlinks. And is this thing really a set? Is there nothing we can do with this? Yeah, it is. Okay, well that sucks. It's probably a bug, at least in the documentation. Let's see. Lazy import glob.noRecurse symlinks. there. I just get added in. This works. This doesn't. So globe not recurse symlinks is still there after it was accessed.
And so is the other one.
And if I import it, it tells me no module named this way. That is... That is bad, actually.
I don't really understand what's happening. Why are there why glob or inspect behave like that?
I think that's probably
imported?
a bug in Python somehow. So when I do import inspect.initGenerator function, it'll tell me module not found there. If I do lazy import, of course in Python 3.15, inspect.initGenerator function, it'll work just fine.
Which one is the bug? Module not found error or the fact that
the fact that this works. So if I go back to CPython,
it's in lib inspect.
where is this imported lazily?
Imported lazily. That's a good question.
Here, the context lib. From lazy from inspect import. Oh, I see. So if you do a new session, lazy from inspect import is generator function, then that'll work. And of course, from inspect import is generator function will work as well. But if you do sys dot lazy modules, well, let's import something else. Right, and we'll put in this entry instead of the actual module name. Well, that's at least a bug in the documentation, because this is not a fully qualified module name. Okay, so if this is a bug in the documentation and it needs to say a set of arbitrary strings that have no meaning, then then we cannot fix Fedora's import checker. If the documentation is correct, then this implementation would be correct as well. yeah, let's. I will maybe find some time to import this. And we can continue next week.
I think we can. I will have time next week.
Okay. So.
Not entirely sure about the full summer. Maybe it will not melt. But for now, next week looks all right.
All right.
Okay.
See you then.
Thank you for today. I'll see you.
Thanks for your attention. See you.
Goodbye.